Good morning, geometry class. So this video here is going to go through the notes from section 5 and the first two examples. Tautologies and contradictions. In the previous lesson, we learned that the truth value of a conditional statement depends on the truth value of the antecedent and the consequence. The truth value of most logical statements depend on the truth values of individual propositions. But are there any statements out there that are true regardless of the truth value of the individual propositions? And are there any statements that are always false, regardless of the truth value of individual propositions? So if you looked at the homework last night and looked at the answer key, the last two examples actually show this. The answer to number 3 was all true. So that is something called a tautology. All right. So if we have a statement that is always true, regardless of the propositions, it's called a tautology. And number 4 was always false. In that last column, everything was false. That's called a contradiction. So I'm kind of taking this time. This section serves two purposes. The first is to just practice doing more truth tables. The second is to really introduce this idea of a tautology, because that's what's useful to us. All right. The logic proofs that we're going to do are going to be based on rules of deductive reasoning. And those rules of deductive reasoning exist because no matter what we plug in for the truth values of the propositions, the statement is always true. So it's part of the reason why we're doing this today is to introduce this idea of a tautology. Okay. Now, tonight for homework, in the two examples that we're going to do a truth table, and at the end, we're going to identify, is this statement a tautology, a contradiction, or neither? And numbers 1 and 2 from your homework last night were neither a tautology nor a contradiction. Sometimes they're true, sometimes they're not. It depends on the individual truth values of the propositions. Okay, so I have two statements here, and I'm pretty sure if you just think about it, you can realize why these would be a tautology. So number 1 says that P implies P. If P is true, then P is true. Or, if P happens, then I guess P happens. It's almost like it is what it is, like that's kind of, people say that, like that's what this means. If those of you have Mr. Sorensen always says it is what it is. And for a while I was like, yep, that's a tautology. And then I just got tired of saying that. Okay, so all right, P implies P. Let's do a truth table for P implies P. And then number 2 says P and tilde P. P and not P. There's no way that can ever be true. We can't have P be true and also not P be true, or P is both true and false at the same time. That does not make any sense. All right, so we're going to do a truth table for each of these things just to make sure that they are, in fact, a tautology and a contradiction. Now, we don't need 4 rows for P implies P, because P is only true or false. So we're going to do a true and a false. If you did true, true, false, false, you're just kind of doing the same work twice. But okay, true implies true. Yeah, that is true. False implies false. Well, that's also true, right? So right, true implies true is true. False implies false is also true. So, yep, that's a tautology. P implies P is a tautology. Okay, and now for P and not P. Well, now I guess I need 3 columns. I need a P, I need a not P, and then I need a P and not P. So we go true and false, false and true. True and false is false. False and true is false. Yep, that is in fact a contradiction. Okay, so I have 2 larger compound statements here. We'll do these 2 together, and then the rest, the other homework assignments, you guys can try on your own. Okay. So the first one says that um, P and Q is logically equivalent to Q and P. Hmm. That's interesting. It looks like I've just switched the order around the caret. So if this turns out to be a tautology, this means that P and Q and P are the same thing. There's something in math called the commutative property that says that if you switch the order around um, an operator and it doesn't change the value, then it's commutative, like addition. P plus Q is equal to Q plus P. So if this turns out to be a tautology, this would show that the caret is commutative, that it doesn't matter if I say P and Q or if I say Q and P. They mean the same thing. All right, let's take a look. Okay, so P and Q is logically equivalent to Q and P. Let's see when this is true. All right, I need a P, I need a Q, I need a P and Q, I need a Q and P, and then finally I need a P and Q if and only if Q and P. Okay, so we go true, true, false, false, true, false, true, false. P and Q is true, false, false, false. Q and P, true and true is true. False and true is false. True and false is false. False and false is false. Well, they do look the same. Remember, logically equivalent, saying do these truth values match? So those match, those match, those match, and those match. Yeah, this is in fact a tautology. All right. So the and statement is commutative. I wonder what other operators are commutative. All right. The next example we're looking at is this complicated one that says that the negation of that and statement implies that or statement. Okay. So I need a P, a Q, a not Q, a P and not Q, a not P and not Q. Whew, I hope I have enough room. A not P, a not P or Q. And then my last statement, which I'll just label with a star because I'm out of room. Okay, so true, true, false, false, true, false, true, false. Okay, not Q is going to be false, true, false, true. P and not Q. Guys, my handwriting gets a little messy. That's a true. That is a false. True and false is false. True and true is true. False and false is false. And false and true is also false. Okay, the negation of that, we're just going to go true, false, true, true. Hey, let me take a time out here. What does this line look like or that column look like? Have you seen that before? This looks like it is the same as P implies Q. So what that tells me is that this expression here is logically equivalent to P implies Q. Not that that has anything to do with this problem. I just thought that was interesting. It might be a foreshadow of things to come. And okay, tilde P is going to be false, false, true, true. Tilde P or Q. So tilde P or Q. False or true is true. False or false is false. True or true is true. True or false is true. Hey, that's actually the same thing. True, false, true, true. That's also P implies Q. So if this were logically equivalent, it would be a tautology. And logically equivalent is the same thing as a biconditional, which means both the original and the converse is true. So if the biconditional is true, either conditional statement would be true. So this is going to be a tautology. Let's just finish it, confirm it, rather than just hand wave it. So I'm going to do this column implies this column. True implies true is true. False implies true is, false implies false is true. True implies true is true. True implies true is also true. So this is also a tautology. Okay. It's interesting that both of these statements have the same truth table column as P implies Q. So they are both actually logically equivalent to saying that P implies Q. All right. So why don't you guys try your homework, or if there's still time, hop on Zoom and you can ask me any questions you have. Have fun.